Okay, all right. So we form this guess. We plug into the differential equation. That results in a little bit of a complex arithmetic problem that we then solve to get this value of t. Keeping in mind that that's the t that goes there. That is the thing that I multiply by my right-hand side to get my solution. So there you go. That's the solution. And there it is. Just recopying. Notice I went ahead and I multiplied the 7 times that t to get that. And at this point, it's just kind of multiplying things out. There's a little bit of a trick to multiplying this out, but we're just really going to do algebra from here on out. So the little bit of a trick is as follows. Notice I have complex times complex. This first complex factor, though, is in rectangular form. This second complex factor is kind of in polar form. And it's just a little clunky, right? I mean, we don't have convenient rules for how to do that. So let's solve that problem. The easy resolution is just take the polar factor and just rewrite it into rectangular form. And now, of course, very conveniently, I have rectangular times rectangular. Multiplying rectangular times rectangular is easy. It's FOIL. You just FOIL it out, right? So real times real is real. Imaginary times imaginary is imaginary. Don't forget I squared is -1. It's real easy to forget that I squared is -1. That minus sign then cancels with that minus sign to give you the plus sign that you've got right there. Everybody good? Okay. All right. Right. Okay, so then that's how you find the real portion. Now, of course, also imaginary times real is imaginary, and real times imaginary is imaginary. That's the other half of the FOIL. And so we are done. We have our solution written in rectangular form. Questions? Feel free. Okay. All right. So now, how does this pertain to? Let's look back at what we were doing this kind of thing for in the first place. Why was I interested in solving equations that look like this? Well, the reason I was interested in solving equations that look like this is because, more to the point, I want to solve equations that look like this. Right? I want to solve that real portion equation. And so, because purple is the real part of blue, the solution to the purple is the real part of the solution to the blue equation. Right? So, just like we discussed in the notes. So, notice the second part of this exam question is, directly connected to that. The second part of the exam question says, let's solve these two differential equations down here. Now, if you don't understand the connection between real differential equations and their sort of equivalent complex differential equations, then you would look at those two differential equations and this one differential equation and just see three differential equations, right? And then, of course, you'd be out of luck because then you'd have to, one down, two to go, right? You'd have to do each one of these separately, and it'd be a big pain. Each one of these separately, by the way, is itself individually a big pain, right? The big idea is to notice that this first equation is exactly, let me do it like this, exactly the real part of that complex equation that we just solved. It's exactly the real portion. And so, likewise, along those lines, this u that I'm interested in is just the real portion of the solution that I just found. So it's a snap of the finger, right? It's a instantaneous. We cite the connection to the complex equation, nothing to it. We don't have to set up an undetermined coefficients. There'd be two undetermined coefficients, and we'd have to take a bunch of derivatives of sines and cosines and have a 2x2 system. And it's a micro pain, but it's still a pain, right? And then separately, then we'd have to do the same thing down here. Of course, having noticed the connection, I can observe that that is exactly the imaginary portion of the differential equation that we just solved. And because it's exactly the imaginary portion, the answer that I'm looking for here is exactly the imaginary portion there. So, what do you think? Questions about that? Feel free. Alrighty. Okay. Okay. So thus ends the flip portion of the course, and we're now going to go on to new material in in chapter 5. We're now into chapter 5, and this will be a traditional lecture in the sense that it's there's no pre-lectures. Of course, it's a little non-traditional in the sense that we're video recording and there's pre-written lecture notes that you all have a copy of, and so there's some there's a bunch of additional features, but no pre-lectures. Okay, so here we go, chapter 5. First, I want to say some things about functions, and I know you all know what functions are, but there's a few things that we just have to get said, bits of terminology, and I just want to make sure we look at functions the right way in some ways that are going to be about to be really important. So if you have a function, I like to think of a function as a kind of a process that takes inputs and then gives you outputs. Right? So for such a function, if you want to describe such a function, we typically give a function a name. Here we're calling the function f. We'll very often write a colon as a way of indicating, okay, I'm about to tell you more, some key details about this function, right? And we're going to take points out of the green set, and we will then return points that are in the blue set. Right? So f goes from x to y is one way you might say that. Okay, so some key terminology. This set that the inputs can come from. The word I want to use is domain. There's different ways that you could describe. I mean, really kind of maybe a more direct way to describe it would be input space, right, or input set. But domain is very common. It's a universally used term. So let's go ahead and get on board with that. So the what you might call the output space, this blue set that outputs from the function have to land in. We're going to use again the common term target. Now, you can kind of think of it as it's the output space. It's the space where the outputs have to land. But the term that we'll use is target. Okay. All right, so this is the most important stuff to know about a function. I want to emphasize that really, if you want to describe a function, carefully, a function is actually a trio. A function is not just a formula. A lot of students think a function is just a formula. A function is a trio. It's a domain and a target and a formula that tells you how to take anything from the domain and get the corresponding output in said target. Okay, so it's the trio together that is the function. Okay, there is a third set that I need to talk about here. This third set is commonly confused with the target, but it is importantly different from the target. This set that I want to talk about is the set of actual outputs, right? So in the picture here, this set B, and just per the picture, let me point out, it does not have to be the same thing as the target. The target's requirement is simply that all of the outputs have to be in the target. It is not required that the function actually fill up the target. So there can be some slack in there, some sloppiness, right? Some looseness there. The actual outputs might just never hit certain points in the target. No problem. Okay. So the actual outputs, though, this set here of actual outputs, it's also an object of interest, and I want to use the word image. So, I mean, it depends on how you think of a function, but, you could kind of imagine, like, if you have a screen here that's your domain, and you're shining a light bulb through the screen, and then there's an image, on this other screen over here, and that kind of conjures, points that are over here in this world get projected over into points over on this world, and so the term image is pretty natural in that metaphor, and common choice of term. So image and target are not the same thing. Let me hit pause real quick. Anybody have any questions about that? I got some examples coming up. Yep.
I guess just like the drawing in general makes it look like the output, like what's circled in yellow is going to be. I mean, what's in yellow isn't the output.
What's in yellow is the collection of all the actual outputs. The blue set is just a set that I promise all the outputs will land in. Right, so the blue set has flexibility. As long as, here's one way to say it, as long as the blue set contains the yellow set, then the blue set's cool.
Is it analogous to span?
Let me say no comment for a moment. There is a connection there, but I don't want to talk about that connection right now. So for the moment, I'm going to say no asterisk, and I'll expand on the asterisk later. Yeah. Okay, so let me go to the examples. I want to talk about the importance of the difference between image and target. So here's an example. So we've got a function here. There's my formula for my function, f of x equals x squared. Now, I wanted to think of that function as defined on R1, so on all real values. Right. So notice no complex values. Right, just real values. And then I am making the promise when I say that the target is R1, I am promising that when I take any one of these domain points, right, any real number, put any real number into here, compute per the formula, what comes out, I promise, will be a real number. Right? Now, that said, it will be a real number, but it can't be just any real number. In fact, I happen to know some things about this formula, right? It will always produce a non-negative number, right? So, okay, that's fine. I mean, that doesn't contradict my promise that they will always be real numbers, right? Just refined further information. It will produce all non-negative numbers, and everything that will come out will be a non-negative number. So the image is exactly the set of non-negative numbers. At which point, a lot of students think, well, then what's the purpose of the target? Like, why would I even talk about this concept here if it's not exactly the set of outputs? And if I know what the set of outputs is, why have this larger sloppy set that seems to half of this larger set seems to serve no purpose, right? So why did we talk about that? So that's the subject of my next example down here. Next example, just another function. Here's a function. Here's a formula for how to compute it, and I'm going to have this as defined on R2, x comma y, right? And I'm going to say that I promise that all the outputs will be real numbers, so I'm going to say the target is R1. Why do we talk about that target being R1? And the answer is because it's super inconvenient to compute the image. The actual image in here, I mean, my gosh, what a pain, right? This is all Cortican stuff. I mean, now let's stretch that out a little bit more carefully. How would I actually compute the image of this function? It's real value, right? So You can also see it's got x to the fourth and y to the fourth. I mean, you can see that the values of this function get arbitrarily large, right? Can the values of this function get arbitrarily small, arbitrarily low? Well, no, they can't, right? Because it curves up in all directions because of the coordinate terms, right? So this is like it's got sort of a lumpy bottom to it, but it's sloping up in a kind of it's like a paraboloid kind of thing, but quartic instead of quadratic. So it can't go to negative infinity. So it's going to have some sort of a minimum value. What is that minimum value? Well, I guess we could find that minimum value. We all took Math 212, right? So you take the gradient and set it equal to 0, and then you realize in taking the gradient and setting it equal to 0, you've got a cubic system of two equations. And a pair of cubic equations is really hard to solve. And so it'd be a tremendous pain. It might even be intractable. I don't want to try. I haven't tried. But that's not the point. The point is, why bother, right? Let's consider why would we be interested in a function like this in the first place. It may be something as simple as, this represents a certain aspect of a physical system I'm looking at, and I'm about to move the dials a little bit, and I'm about to make some changes in the input, and I just want to find a directional derivative. As I make certain changes to the inputs, I just want to find certain changes, what's the corresponding changes in the outputs. I just want to compute a directional derivative. I don't care about the minimum value. I don't care about the image. The image serves no purpose in what I'm doing. Right? So in this case like this, when I don't care about the image, it's very nice to just be able to say, look, what comes out are real numbers. Which real numbers? Not my problem. But what comes out are real numbers. That describes what kind of a function I'm talking about. I mean, the objects that come out of here are that kind of thing. Very convenient to just be able to say, okay, so the target is R1. Okay, what do you think? Anybody have any questions about that? Okay. All right. Oh, excuse me. Okay, so let's finally get around to defining the fundamental object of interest now for this section and really the rest of this chapter. We define something called a linear transformation. In fact, we've seen a bunch of linear transformations before. We just haven't written down the definition. So let me write down the definition, and I'll remind you of linear transformations we've seen in the past. A linear transformation is a function. It's a function t. There's a few requirements. The domain has to be a vector space. That's the first rule. The target has to be a vector space also. That's the second rule. Those are easy to check most of the time. The third rule, the linearity condition, that which makes it linear, I'm going to write down as this rule right here. Now, hopefully this will be a familiar construction. Let me remind you, easy first example, when have we seen linearity in the past? Most recently, we saw linearity when we were talking about linear differential equations. And the idea, remember, is that linear means that when you put a linear combination of inputs in, you get the corresponding linear combination of outputs out. Right? So linear combination in, linear combination out. Or I think I used the term, it plays nice with linear combinations. Okay, so those are the three rules. The domain's a vector space, the target's a vector space, and the function satisfies the linearity condition. Okay, so examples where we've seen this in the past. One of them I just mentioned in chapter 4. Right, when we were talking about linear differential equations. We went to some trouble to talk about how you can take that whole monstrous left side of the differential equation, and that monstrous left side of the differential equation, you could let's call it L. Right? That's L of y. And this L thing had the property, as we described it at the time, of being linear. It's exactly this. Okay? We talked about linearity back in chapter 1 when we were talking about this property called multilinearity. You all remember multilinearity of determinant, and the idea is that if you think of determinant as a function of one vector at one row at a time, for example, maybe one column at a time, your preference, doesn't matter. Let's take it one row at a time. Fixing all the rest of the matrix and thinking of only one row as actually being variable. Determinant is linear. And we talked about how if you put a linear combination of inputs into that row, you get the exact same linear combination of the corresponding outputs. Right? So that linearity, that's this exact same notion of linearity. All right, so we've used it before. We just never got around to defining this word. The word being linear transformation. These functions are linear transformations. Okay. Everybody good? All right. Okay. Some things that you can check for yourself. These are exercises. If you're interested, it's a good exercise. Everybody should do these. Any function that satisfies this condition also satisfies this condition. And it seems like this condition I have circled in blue must be a stronger condition because after all, this condition in blue means that you can, linear combination in, linear combination out, but even for combinations of more than two vectors. This is combinations of any number of vectors. Seems like this is saying more than that is. But in fact, these are equivalent conditions. Any T that satisfies this property also satisfies this property. I'm going to leave that as an exercise, again, for you all to check. Here's how you're going to do it. You're going to take this thing on the left, and you're going to simplify it by using this property and show that as long as T satisfies this property, this expression here can be rewritten, what you might call one term at a time in the linear combination, to be this expression. Okay. So that's, like I say, a nice exercise for you all to play with. Here's another equivalent formulation. Some books make this the definition of linear transformation. It's the combination of that condition and that condition. So, good news, bad news. The bad news is obvious. There's two conditions to check. Right? Who wants to check two conditions when you could instead just check one condition? On the other hand, each one of these conditions is arguably easier. Here, it's just addition. You add inputs, you add the outputs. Wow, that's really... Right, that's much more sort of like relatable in a way. Likewise, over here, you scale the input, you scale the output. Very relatable, very kind of, it's just a lot less to write down, you might say. So it's a pro-con kind of a deal. And now, I'm going to leave it as an exercise for you all to confirm any function that satisfies the purple property also satisfies both of these green properties, and vice versa. Any function that satisfies the green properties, both of them, also satisfies the purple property. So it's a matter of, again, just, using whichever one you're assuming to prove the others. And come to office hours if you have any questions about how to do that. Which one should you use to prove things with? It's kind of up to you, but I'll tell you, my experience is that it tends to be easiest to prove with this one. But it is, on the other hand, very nice. Once you know that you have a linear transformation, it's very nice to be able to cite the blue one. And sometimes it's very nice to be able to cite the green ones. So anyway, there's that. Okay, now I want to talk a little bit about terminology. So this statement right here, well, let me go back to the color. So this blue statement right here. Sometimes people say that such a function commutes with linear combinations. This is a kind of a little bit of micro abuse of the term commutes. Now let's talk about that a little bit. So this term commutes. What does it mean for something to commute? Y'all have seen, perhaps as early as elementary school. When I was in elementary school, they made me learn, the commutative property of addition and the commutative property of multiplication. Did they make y'all do that same thing? It's like, oh my gosh, why? It's so obvious. Of course, A times B is B times A. It seems so crazy obvious. Anyway, the idea then is commutes means you can do them in either order and it doesn't matter. Right? So notice that's kind of what this linearity property says between the function and the linear combination. Here we're doing the linear combination first, and then we're doing the function second. Right? Over here we're doing the function first, and then we're doing the linear combination second. Right? So it's kind of like, it's not like I say, it's not exactly commuting because we're not multiplying, right? These are two fundamentally different things, but it's got that same, right? Structurally, it smacks of you can do it in either order and it doesn't make any difference. And so it feels like commuting. And so the intent, I think, is actually quite clear. If you say commutes with linear combinations, that's what people are referring to. And it's a nice way to think about the linearity property. It's very succinct. It commutes with linear combinations. Okay. All right. Okie dokie. All right, some more lingo I want to talk about. This next page of notes comes from a conversation that I had a couple years ago with the professor who has taught Math 353 many, many times, more probably than anybody else in the last 20 years-ish. So he came to me and was, sharing a kind of a frustration of, students know what a linear transformation is, right? Of course, students will get out of this course and know what a linear transformation is, but he felt like students didn't know what the word linear meant, right? In all the ways that the word linear gets used. The point here is that linear gets used in a lot of kind of slangy, kind of sloppy kind of ways, right? In ways that are very convenient, and that where there's no ambiguity of what the speaker means, but nevertheless it's not exactly quite strictly the way that we've defined the term. So what I want to do is I want to go through a few examples of ways that you're going to see the word linear pop up. And I want to help you understand how you're supposed to interpret it when you hear it in these different, very different usages in different situations. So here we go. A matrix acts linearly on vectors by left multiplication. Like so. Okay. All right. Now, here's how you're supposed to interpret this phrase. First of all, notice the word linear. Linearly here. When you see that word linear, what you should do is a two-step process. The first step in the process is, in recognizing that the word linear has been used, you should identify, okay, somewhere in this story, somewhere in this sentence, this description that's being made here, there is a function. So your step one is to identify what is the function that's part of this story in which the word linear is being used. Okay? And so, you can see the function right here. The function is that. By the way, that's the same function that we talked about back in chapter 1. Remember, we reinterpreted matrices as functions, and interpreting a matrix as a function was very helpful in understanding determinants, right? Making certain key geometric interpretations of determinants. So that's the function, right? And it's exactly the function that's described in the language. This is what matrices do, right? Think of acts as this is what they do. Matrices, what do they do to vectors? This is what matrices do to vectors. You multiply on the left of the vector, right? So that's the function. Step 2, having identified the function that is part of, whatever's being said there. Interpret that what the speaker meant was to say that function is a linear transformation. All right. So when the speaker says matrices act linearly, and by the way, it might be as brief as that. It might be that the speaker says just this: matrices act linearly, or maybe even maybe a little bit more. Matrices act linearly on vectors. Right. This succinct. Matrices act linear on vectors. What they're saying is that if you interpret a matrix as a function, that this function that results is a linear transformation. Now you can count syllables, right, in what I just said versus A acts linearly, and you can see the appeal, right? It's just a lot easier to say matrices act linearly and let the listener interpret. Oh well, he's talking about a function clearly, and linearly means that the function that he's talking about must be a linear transformation. Let the reader interpret all of that, right? And it's just very handy, and that's how people talk, right? So when you go on beyond Math 216, and I'm probably going to capitalize on this in this course as well, but that word linearly, and it pops up in a bunch of different ways. Whenever the word linear pops up, identify what's the function that's being discussed and interpret that they're talking about a linear transformation then. So here, projections down to planes containing the origin are linear transformations. It's a lot easier to say projections are linear than it is to say the function that's defined by projections to a plane containing the origin are linear transformations. It's a mouthful. Right? Projections are linear. Much easier. The word linear operator, don't worry about this notation. But we talked about linear operators back in chapter 4. This was an example of, L of F is the way we wrote it at the time. Right? So this is a linear operator. What we mean is that this function from C2 to C0, perhaps, that this function is a linear transformation. But we'll just put the word linear in there as an adjective and go about our business. Call it a linear operator. Okay, so we're out of time. We'll call it a day right here, and see y'all on Wednesday.